Okay, so we are going to be working on a few problems here for lecture day number 1, worksheet number 1. So I'll just jump right into it. If you've already been in the discussion, then you may have already seen these, but I will do more examples. So you can feel free to skip ahead in the video. So example number 1 is just solving this equation. The first thing that you can do for this equation is to multiply both sides by the least common denominator, which in this case is 4. So I multiply by 4 on both sides. 4 times 1/4 is going to cancel out that factor of 1/4, and you get a factor of 1. Then we multiply 4 by our -2, and then we'll multiply 4 by the 1/2. And so this is going to give us n plus 8. The 4 and the 1/4 canceled, minus 8 is equal to 4 times 1/2 is 2, and minus 6. And then we have the positive 8 and the negative 8, they cancel. So we get n is equal to 2n minus 12. And so subtracting the 2n on both sides gives us a negative 1n, which is equal to negative 12. And dividing by negative 1 gives us n is equal to 12. Okay, so in this case here, there is exactly one solution. We got our variable equal to a single value. So that's just our only solution. Example number 2. We have, I'll write it down below, 2 times x minus 4 plus 10x is equal to 8 plus 4 times 3x plus 1. And so with this equation, we can distribute. We have 2x minus 8 plus 10x is equal to 8 plus 12x plus 4. And if we combine like terms, on the left-hand side, we have 12x's and a minus 8. On the right-hand side, we have 12x's and a plus 12. And so if we were trying to solve for x, we would try to get all the x's on one side. I want to subtract 12x to get rid of the x on the right-hand side. But it turns out that on the left-hand side, the x's also cancel, and we get negative 8 equals 12. We've eliminated the variable, and we ended up with a false statement. This implies that there is no solution. The solution set, we could say in this case, the solution set is what we sometimes call the empty set. This is a set where, there's nothing in it. It's empty. Another notation for the empty set is, it looks like a 0 with the line through it. The solution set for example number 1, if we wanted to write that out, is just the set containing the value 12. It's just a set of one value. So normally it's not written that way for when you have one value, because, well, you could just write the number n equals 12. That's your solution. Okay, so example number 3. Five x minus 9 minus 2 is equal to negative 5 times 2 minus x minus 1. We can distribute on the right-hand side. And on the left-hand side, we can combine like terms. So we get 5x minus 11 is equal to negative 10 plus 5x minus 1. If we, well, the left-hand side, there's nothing to do. The right-hand side, we can combine the 10 and the negative 1, 5x, 10 and negative 1, negative 10 and negative 1, make negative 11. And so again, if we were to try to, let's get all the x's on the left-hand side. So we'll subtract 5x from the right-hand side. We have to do the same thing on the left-hand side. It turns out that they cancel. And so in this case, now we get, again, we've eliminated the variable completely, but now we get a statement that is true. Negative 11 is equal to negative 11. And so this implies that there are infinitely many solutions, but we can actually say something even better than that. Not only are there infinitely many solutions, but all real numbers are solutions. The solution set in this case is going to be an infinite set containing all numbers from negative infinity to positive infinity. And sometimes, just like the empty set, there's a zero with a slash through it. There's a special notation for all real numbers, and it's this fancy looking R. Okay. Now a quick definition. This is on the worksheet, I believe, but it's important that we know what the absolute value means, what its definition is. So we say that the absolute value of a number A is the distance between the number A and 0, the number 0 on a number line. Okay, so as a couple of examples, here little quick rapid fire examples, I could ask you, what's the absolute value of, 3? And you can just draw a number line and say there's 1, 2, 3 spaces between 0 and 3. And so the absolute value of 3 is 3. The absolute value of negative 2 is 2, right? Negative 2 is 2 units away from 0, and so on. So the absolute value is usually positive, but there is one case where it's not positive. The absolute value of 0 is not a positive number. This is 0. Okay, so then from this, we can say just a quick little remark. The absolute value of A is always greater than or equal to 0. That may come in handy later in the worksheet. And so let's jump into a couple of examples. Example number 4, example number 4 here. Yeah, let's make these a little bit more complicated than what I gave in class. So just slightly here, we'll do 2 times the absolute value of x plus 1 is equal to 7. How about that? So here's an absolute value equation. Now, for many of these absolute value equations, we want to isolate the absolute value first. So we subtract 1 on both sides, and we have 2 times the absolute value of x is equal to 6. And then we need to divide by 2 on both sides. And that would give us the absolute value of x is equal to 3. Now, this is where we need to think a little bit about how we deal with this absolute value in this equation. We are asking for, we're basically looking for any number whose absolute value is 3. That's what x is. X is any number whose absolute value is 3. And so earlier we said, well, that means that x is equal to 3 because we said that the absolute value of 3 is 3. So x is either 3 or we have another solution, x is equal to negative 3. These are your two solutions for this equation. So more generally, we can give a rule here. I think I called it rule 1 in the lecture. And that is that it's that if you have an absolute value of some expression, ax plus b, and you have it set equal to c, then this absolute value equation is equivalent to just like we did earlier, we basically just dropped the absolute value, ax plus b, equal to that number, c, equal to 3 earlier. And then the other equation that we can get solutions from is to take this equation, drop the absolute value, but then change the sign of the number that's on the other side. So, or, it is important that we have that or there, ax plus b is equal to negative c. So this is the rule that we can use when tackling equations involving absolute values. Okay, good. Now let's go ahead and move on to another example. Example number 5. The absolute value of x is larger than 2. Or actually, you know what? I'll use 3 in this case. The absolute value of x is larger than 3. We want to describe the set of numbers whose absolute value is more than 3. So the numbers that are more than 3 units away from 0. And so if we draw a number line, we can find those numbers. Actually, in one of my classes today, somebody said that that would be 1, 2, 3, 4. You know, the numbers 4 and greater, right? But it turns out that there are more numbers that we're missing if we say 4 and greater, because what about 3.5 or 3.4? Those numbers have absolute value larger than 3. And so we have then, you know, all the numbers basically up to 3, but not including 3 and greater. And then similarly, we have numbers, you know, towards negative infinity up to negative 3, but not including negative 3. So if we were to write this out in terms of inequalities, this is x is greater than 3, or our solutions can be found with the inequality x is less than negative 3. And so here is one way to write the solutions to this absolute value inequality. With all of these absolute value inequalities or equations, we eventually need to turn the equation or inequality into a statement that has no absolute value. And so that's what these rules do. So this absolute value inequality becomes, I'll put an arrow here, it's equivalent to x is less than negative 3, or x is greater than 3. And so we kind of need to see how, you know, how we got these inequalities. One of them, or how we can get them for later problems. One of them is essentially the same as the original, but you drop the absolute value. Then the other is we change the sign, we flip the inequality sign, and then we change the sign of the number. You know, the positive 3 became a negative 3. Okay, so then this will give us our rule, which I'll call rule number 2. And it says that the absolute value of ax plus b greater than c is equivalent to the two inequalities, or the compound inequality, ax plus b is greater than c. We drop the absolute value symbol. That's one of our inequalities. Or, it is very important that you have this or here, ax plus b is less than negative c. So just like in one of our inequalities earlier, we flipped the sign. So we flipped the sign, and then the positive 3 became a negative 3. The c becomes the opposite of c. And this rule, I guess we could say, this applies if c is greater than 0. greater than, let's put it or equal to. Same thing here. This rule really applies if C is greater than or equal to 0. Okay. Very good. Let's take a look at example number 6. Oh, and actually, before I do that, we've written our, inequalities. We could also write this solution set in interval notation. And so this is going to be all numbers less than -3. That would be from -infinity up to -3. Or the union symbol takes place of the or statement. And then all numbers larger than 3 would be from 3 to infinity. So there's another way to display the solution. Interval notation, you can write it as inequalities, or you might see a graph of it. All right, moving on to example number 6. Example number 6, the absolute value of x is less than, let's do less than 3. Less than or equal to, I'll put. So we'll start with a graph again, because a lot of times they give us good insight on, what the solutions might be. 1, 2, 3. So here we're asking for all numbers within 3 units of 0, closer than 3 units or exactly 3 units away from 0. And so that would be all numbers between -3 and +3. And then I color in these circles here because now we're indicating that we're including not only between -3 and +3, but also including those end values, endpoints, -3 and +3. And so one way to, show this information essentially, one way to do it would be to write down this inequality, x is less than or equal to 3. So we want numbers that are less than 3, sure, but we don't want to go too far below 3, because if you go too far, like -4, its absolute value is not less than 3. So we also need these numbers, our solutions, or the numbers that will be part of our solution set also need to satisfy x, that number, being larger than or equal to -3. And so we're going to need both of these inequalities to be satisfied, not either one or the other, but we need both of them to be satisfied. So we need an and statement here. We need the number to be less than +3, and we need it to be greater than -3. And that will give us exactly this set of numbers, greater than or equal to -3. I think I misspoke there. So contrast that with the previous problem where, the number can be less than -3, or if it's not less than -3, it would be part of our solution set if the number was greater than +3. Okay, so there's a big difference there between the or statement and the and statement. It is important that you know the difference between those two. And I've got a few minutes before I have my next meeting. So I'll do, let me write a couple more things down and then I will try to do some quick examples. Okay, so this is one way to write the solutions, the set of solutions in, using inequalities, but we can also write these solutions or indicate what the solutions are with a compound inequality. Some textbooks will say the absolute value of x is less than or equal to 3, and this is equivalent to x is less than or equal to 3, and then they'll put another less than or equal to sign on the left-hand side of x, and then put that -3 on that side. So what this says is that x is greater than, because the symbol is opening towards the x, so x is greater than or equal to -3, and x is less than or equal to +3. That's exactly what we set up above in two inequalities with the and, joining those two inequalities. So whichever one of these two you want to use, both of them indicate the exact same set, the one that's graphed there in black. Okay, the interval notation for this, oops. Is going to be the set from of values from -3 to +3. It would be incorrect if I put a round parentheses here, because we have that or equal to in this problem, so we need a square bracket. So there we go. That is the interval notation. All right, so let's take a look at, an example. I'll try to do an ugly one. Yeah, maybe I can do a few quickly. This is just for, anybody who wants extra practice. So we'll do example number 7. The absolute value of 2x minus 7 divided by 5 is less than -1. The first thing that you can do here is multiply both sides by 5. And so we get the absolute value of 2x minus 7 is less than -5. So we've isolated the absolute value symbol. And now we need to try to see which rule could we use here. Notice that we have a less than symbol. And so we should use the rule from the that we gave. Oh, and I didn't write rule number 3, so let me go ahead and write that down. But essentially, rule number 3 comes from this absolute value being less than some positive number. We'll use the rule from example number 6, and let me write it down actually. So rule number 3, and that is that the absolute value of ax plus b being less than or equal to, all right, for this one, some number c is equivalent to ax plus b less than or equal to c, and ax plus b being greater than or equal to -c. Okay, so let me go ahead and let's try to apply that rule to this inequality here, right? Notice this inequality has a less than symbol, and so it's definitely very similar to this inequality here with the less than. So we'll use this rule here. We'll try to write out these two inequalities and see what that gives us. The first inequality would be 2x minus 7 is less than -5, and 2x minus 7 is greater than the opposite of this number. So the opposite of -5. We could just write +5 because we have a minus or opposite of c. I'll write it as the opposite of -5. We'll simplify that. Okay, so then now we solve this inequality. We can add 7 to both sides. We get 2x is less than 2. Dividing by 2 on both sides, we get x is less than 1. Now remember, we have this and here. So we can add 7 to both sides. Remember that this is a +5 really, so we'll get 2x is greater than 12. And then dividing by 2, x is greater than 6. And so, 1 second here. Oops. All right, sorry about that. Hopefully that, oh no, hopefully that comes out in one piece. Okay, anyways, so we were wondering what the solution set is here. So what numbers are less than 1 and greater than 6, right? Less than 1 would be in this direction, greater than 6 would be in that direction. Are there any numbers that are in both of those sets of numbers? Remember, we have an and here, which means our solutions have to satisfy both of these inequalities. There is no number that is both less than 1 and greater than 6. So that means, let me erase this here because it maybe it looks a little misleading, like that's the solution. A solution would be a number that's in both of those sets. There is no such number. So in this case here, we would say there is no solution. The solution set is empty. We could also just, put this little 0 or do the curly braces, with nothing in them. All right. One way that we could have seen that, and this actually comes up on the worksheet, is that if we had kind of kept a sharp eye open here, and we had looked at this inequality carefully, remember that earlier we said in this remark that the absolute value, if you have an absolute value on one side of an inequality, that is by itself going to be larger than or equal to 0. And so in this example, we essentially were saying, there's going to be will there be x values such that the absolute value of this expression, which we know is larger than or equal to 0, is that ever going to be less than -5? Well, if we know that the absolute value is always larger than or equal to 0, then the absolute value cannot be less than or equal to less than -5. Okay, so that right there told us, that there was no solution. We could have stopped at that point and said no solution. But I wanted to work it out with the rule because, you could try it out and see what it gives you, but it gives you something that makes no sense, right? There are no numbers less than 1 and greater than 6. And that's why earlier, and I forgot to do it on rule number 3, I would say, this rule applies if that number on the right-hand side, C, is greater than or equal to 0. If C is greater than or equal to 0. Because if that number is negative, like that -5 is, then the rule, yeah, sure, you can use it, but that's a case where, you may have no solutions, or yeah, actually we used it there and we said there's no solution. Okay, and it looks like my meeting person is not here yet. So maybe I'll do another example and just stop when they get here. Example number, what number is this? 8. The absolute value of 2c plus 3 minus 5 is less than 1. So here, we want to isolate the absolute value. So we can add 5 to both sides. And we get the absolute value of 2c plus 3 is less than 6. Now, this is another less than 1. So we're going to use rule number 3 again. And this single absolute value inequality is going to become 2c plus 3 less than 6 and 2c plus 3 greater than -6, right? We're applying rule number 3 here. Basically, one of the inequalities is where you drop the absolute value. The other one, you switch the sign and you change the sign of the number on the other side, and you put an and statement there. Okay, then we just solve each one of them. We'll try to quickly solve. 2c is less than 3. And so we divide by 2 on both sides, we get c is less than 3 halves. And if we subtract 3 on the right-hand side, that inequality, 2c is greater than negative 9. Dividing by 2, we get c is greater than negative 9 halves. And so, 3 halves is 1.5, negative 9 halves is negative 4.5. And so now it looks like, well, let's go ahead and graph actually. What numbers are less than 1.5? Here's 1, 2. So 1.5 is here. And greater than negative 4.5. 1, 2, 3, 4. I'll go to 5. 4.5 is here. So we want all numbers, not including negative 4.5, greater than negative 4.5, but less than 1.5. And this is a graph of our solution set. Okay. The interval notation is going to be from negative 4.5. And I made a little mistake there. We need a round parentheses instead of a square bracket. And then we go up to 1.5, again with the round parentheses. All right. Okay, let's take a look at another one. Example number 9. We have a negative 1/3 times the absolute value of 3 plus x over 2 in absolute value less than negative 2. So in this case, we can multiply. Since we have a fraction, I can multiply both sides by 3 to get rid of that fraction. Actually, let me multiply by a negative 3. Since that's a negative 1/3, the 3's are going to cancel, the negatives cancel. And then if you remember, hopefully you remember from a previous class, that when you multiply an inequality by a negative, this inequality symbol needs to kind of flip. So it was a less than, it becomes now greater than. Oops, yes, greater than. We're going to flip it around. And then we multiply negative 2, negative 3, that's positive 6. And so now we have an inequality with a greater than symbol. That is, rule number 2. We want the absolute value of some expression to be greater than 6. Then we need that expression, 3 plus x over 2 to be greater than 6. Or if 3 plus x over 2 is less than negative 6, that would give me solutions as well. So now we have 2 inequalities that we need to solve for x. They have a fraction in them as well. So I'm going to go ahead and multiply by 2. Oops, that's multiplication by 2. And I'll solve both these at the same time. So we have 6 plus x over 2 times 2 is just x greater than 12, or 6 plus x less than negative 12. And so for all of these, we can subtract 6, and so we get x is greater than 6, or x is less than negative 18. On a number line, I won't do this one here perfectly, but 0, we have negative 18 somewhere out here. 6 is somewhere right here. And so we want all numbers that are greater than 6. That would be all numbers to the right of 6, not including 6. and all numbers, or all numbers less than -18. And so there's our graph. Our interval notation looks like this: -infinity up to -18. Union takes the place of the or, 6 to infinity. And this is our solution set. Okay. And our last example for today. Let's go ahead and take a look at example number 10. I'll try to fit it here. -3 times the absolute value of w over 2 plus 4 minus 1 is equal to -4. So this is going to require rule number 1 because it's an absolute value equation, right? It's got an equal sign. And so we first need to isolate the absolute value. So everything that's outside of the absolute value, let's get it all on the other side of the equation. So we can add 1 to both sides. We have -3 times that absolute value. Then we can divide by a -3. And so we have the absolute value of w over 2 plus 4 is equal to +1. Now, the absolute value of w plus 2 is going to, w over 2 plus 4 is going to be equal to 1 if w over 2 plus 4 is equal to exactly 1, or if w over 2 plus 4 is equal to -1. And now we can solve both of these equations. I'll solve them by just subtracting 4 on both sides. So we get w over 2 is equal to -5, and w over 2 is equal to, here we get -5, the other side should be -3, or the other equation. If we multiply by 2 on both sides, then we have w is equal to -6, or w is equal to -10. Our solution set is going to be the set containing, let me write it as x. There's a symbol I've seen in the textbook. X is in the set, or today's a Monday here, so w is in the set -6, -10. So our solutions are -6 and -10, right? That's another way to write it. We could graph. That's not going to be too interesting since it's just going to be 2 dots at -6 and -10. So here's our solution, right? There we go. All right. And it looks like those are all of the examples that I had. Yeah, so hopefully this helps a little bit. And yeah, I'll see you in class next time.